recording. Okay, so as I'm sure you're probably curious to know, I have not graded the exam. I am still in the process of doing that. I hope to get that graded sometime this week. So yeah, a little bit on logistics. So you all submitted homework 5.1 today, and maybe for the first time ever, I'll use this chalkboard. So the whole purpose of that assignment is if I have a coordinate system, right, and I have some region, and the region in that case was a triangle, right, and the triangle was h tall and b wide. The idea, oh my, it's tilting on me. Okay, I'm gonna stop tilting. I'm going to stop writing after that. The idea was to figure out where the centroid was of that given region, and the purpose of that assignment was this. Look, that's a triangle. That's a simple region. What we're going to be dealing with is stuff like this that isn't so simple, okay? And what we're going to be doing is using what are called centroid references. You'll find them in your textbook. You'll find them in the FE reference manual. I'll talk about that here in a bit. But I wanted you to respect where they came from, okay? And so when I pull some random formula out, like the centroid of a semicircle is 4r over 3 pi, where'd that come from? It came from this, so that you had kind of an idea of where that stuff came from. Today's lecture and today's exercise is probably one of the more important exercises in the course and in engineering in general. Just being able to locate a centroid of a composite shape is a really, really important skill. It shows up in all sorts of areas of engineering, solid mechanics, fluid mechanics, civil, mechanical, biomedical, you name it. So I want to make sure that you all are comfortable with this. Fortunately, it's also pretty easy. I'd say of all the topics that we do in here, I think this is probably one of the easier topics that we deal with in this semester. As long as you're consistent with your bookkeeping, this isn't too bad. With that, let's just get right into it. So it feels like ages since I've talked about this because I pre-recorded this lecture before the second exam and before our ABET visit, so it feels like ages since I've talked about this. But the spirit of the first lecture that I gave on centroids, the one that was pre-recorded, was that, you know, as analysts, we're interested in determining the center of gravity, which is basically the place that we can place a single vector representing the weight of a given object so that it will have the same force and moment equivalency. And so we find that by taking, so for instance, if I'm looking at x bar, that x bar location is just the sum of the weights times their distance x, that's sort of the moment, divided by the sum of the weights, right? And this is looking at it from an algebraic perspective. This is looking at it from a calculus perspective. However, in engineering, we often deal with objects that are made of a single material, or we might deal with objects like cars or bridges or what have you that might be made of different materials, but it's easier to deal with those materials one at a time. And so instead of looking at it from a weight and forces standpoint, we look at it from a geometry standpoint. And instead of looking for the center of gravity of weight, it's like we're determining the center of gravity of area or the center of gravity of volume. And instead of using the term center of gravity, we use the term the centroid. And so this is what we're going to be looking at today. What you did was an exercise deriving some formulas. Today we're going to use them, okay? So in our last assignment, that was the whole point, was to derive the location of the centroid of something basic, but something that's not like a rectangle or a circle where it's pretty easy to see where the centroid is just by observation. So what you should have gotten from this assignment was that this distance was 2/3 of b and this distance was 1/3 of b. Whenever you're looking at a triangle, the centroid is always 1/3 from the big end, from the bigger end. So that and you're going to see that reference here in a bit. I think it's really important for you to understand where the formulas come from, but I'm really more interested in your ability to use them. But for most practical problems, we tend to just use the expressions that are readily available. One thing that's worth mentioning is that engineering software packages like AutoCAD, for example, can compute a centroid directly. I might show you that near the end of the lecture, although AutoCAD can take a little bit of time to boot up. So we'll see how our example goes. This is a centroid reference. If you open your textbook, this is probably like in one of the appendices. If you have a hard copy of the textbook, it's probably in the cover of your textbook. You can Google this. If you're planning on taking the FE exam, whenever you take the FE, you're given what's called the NCES reference manual. It's basically just a list of formulas, equations, and values that you get to use throughout the exam, and these are going to be available in that exam to you. This is some pretty basic stuff. Like, for example, here's a semicircular region. We're actually going to use this one today. So here's a semicircular region. If I want to determine, say, y bar is computed as 4r over 3 pi. You can see that right here. You can also see the area of the region. We have, circular regions, elliptical regions. Here's a triangle, and you can see that y bar distance is h over 3, same thing as what we got over here, and so on and so forth. What we're going to do is I'm going to show you an algorithm for computing the centroid of a sort of complicated shape like this, and I propose that the easiest way to handle it is to break it up into a series of basic shapes. And as long as you're referencing everything from a common coordinate system, it's actually pretty straightforward to locate the centroid, okay? Now, when you're computing the location of centroids, you got to be careful of a couple of things. So number one, holes are taken as negative areas. So for instance, in order to compute the centroid, you have to use this formula right here, the sum of AX over the sum of A, okay? So if I look at this shape right here, this shape I would say maybe is comprised of 3 regions. There's a semicircular region right here, there's a rectangle right here, and then there's this circular region, but that circular region is a hole, right? So I need to recognize that that area is negative, right? So I have a positive area here, a negative area here. I also need to make sure I'm consistent in terms of my coordinate system. So whenever you're defining or locating the centroid, one of the first things that you have to do is you have to pick a common coordinate system from which to express that centroid. So for instance, for the triangle, that I have here on the board, what I'm interested in is where's the centroid? Well, it's right here, okay? Well, what do you mean right here? How do I get that? Well, if I put my coordinate system right here, like right here at this end of the triangle, then the distance is 2/3 or the distance is 1/3. You have to have a common coordinate system from which to express your values. So as long as you respect that coordinate system, you'll find the process is pretty straightforward. The other thing to watch out for is symmetry. So if you ever have a shape that exhibits symmetry, then the centroid lies along that axis. So for instance, if I'm looking at this trapezoidal region right here, the question is not where the centroid is from left to right. I can tell you where the centroid is left from right. It's somewhere along this line right here. The question is how far up. So if you ever have a shape that exhibits symmetry, don't bother with trying to compute the location of the centroid along that, that region of symmetry. Another thing to keep in mind is that the centroid does not have to lie on the shape, okay? So for instance, if I had a donut, where's the centroid of the donut? It's in the middle, right? It's not actually on the shape, okay? So that's something to keep in mind. Again, I think you're going to find this is really important, but it's also pretty easy. I want to determine the location of this centroid right here, or sorry, of this shape right here. I think you're going to find, again, this is pretty straightforward, pretty simple. I'm going to, in this example, split this shape up in what I would call the easiest way I think possible. But I want you to recognize that there's actually multiple ways that you could split this shape up, multiple ways that you could divide it up and partition it. And in the end, it doesn't matter as long as you are accounting for the full amount of area and all of your bookkeeping and whatnot is done correctly, you will get the same answer. Another thing that is worth mentioning on this problem is that the coordinate system has sort of already been defined for us. So for instance, whenever we compute the x comma y coordinates of the centroid, it's going to be with respect to this point right here because this is the origin. Here's the x-axis, here's the y-axis, and it passes through that point right there. So all of our distances, all of our values, all of our coordinates, and so on and so forth are going to be with respect to that point right there. If you're an engineer in charge of determining the location of a centroid, often the coordinate system isn't given to you, so you have to establish one. As long as you're consistent, though, I think you'll find this is pretty straightforward. Okay. Again, I'm sort of excited to just sort of dive right into this. I think you're going to find also, again, this is pretty straightforward. Okay. So what we're going to do here with this shape is I really like this problem because it employs a lot of the different regions that we as engineers deal with. Like if you can handle these 4 shapes, you can handle pretty much any centroid problem I'm going to throw at you. Okay, so I'm looking here at this cross section here, and I see a lot going on. I see some triangular regions, some circular regions. I also see a hole right here. Okay, so what I want to try and do is I want to try and start mapping out how I want to approach this problem. So I cheated a little bit. I copied the region down here. Okay, and you notice here I got a centroid reference here I'm going to refer to here in a bit. I've got this region here. Here's how I'm going to handle this, okay? Now, I've got this circular hole here, okay, so I'm going to handle this off to the side. So the first thing I'm going to do is I'm going to assume, let's assume that this hole doesn't exist. So I want to redraw this shape, okay? I'm going to redraw this shape as if the hole doesn't exist. So it sort of goes like that, that, and that. Okay? Now, barring my incredibly horrible artwork right here, okay, I'm going to split this up into a series of what I would call simple shapes. Okay? So what we'll do is we'll split this like this, and let's number them. Let's call this shape number 1, let's call this shape number 2, and let's call this shape number 3. So let me describe these. So shape 1 is a rectangle. Shape 2 is a triangle. Shape 3 is a semicircle. But I'm forgetting something. What I have to do is I have to add something. I have to recognize that there's a hole in this section. So what we'll do is we'll say, I need to add to this shape this hole. So we'll call this 4, call this circular hole. And so the idea from a sign standpoint, just think about this in terms of area. If I treated these 3 areas as positive, but I treated this area as negative, think about this like it's Legos, like it's building blocks. I'm trying to construct this, this piece here. So I take the rectangle, I take the triangle, I take the semicircle, and then I take this hole out of it. That gets me to this piece right here, right? Make sense? I think that's probably the easiest way of splitting this up. I have split this up into 4 shapes. I could split this up into 100 shapes. Like, for example, this rectangular region in the middle, this area number 1. I could take region number 1, and instead of 1 rectangle, I could turn that into 2 rectangles, or 6 rectangles, or 87 rectangles. It wouldn't matter because it's all the same region. And as long as you're accounting for everything, you will get the same answer at the end of the day. I just think this is the easiest way to split it up into as few shapes as possible. Okay? So everybody sort of with my strategy so far? Okay. Now, whenever I compute centroids, I tend to do it in a tabular fashion, okay? So what I'm going to do here, and I'm going to cheat a little bit because I kind of want to move this note over here to the side, I'm going to take this, move this down a little bit. I'm going to take this, maybe move it up like that. Okay. All right. I probably didn't achieve the intended effect, but it's close enough. All right. What I'm going to do is I'm going to draw myself a little table right here. Okay. And it's going to be kind of long. There's going to be like 6 columns in this table, so just be ready for this in your notes. Okay. So I'm going to. Oh, I meant for that to be a pen. So let's start off with region. And I'm going to have 1, 2, 3, 4. Okay, so there's 4 regions here in this cross section. All right. The first thing that I'm going to do is I'm going to compute the area of these regions. Okay, let me see if I can scroll down a little bit. Let's do that. I think you're going to see where this is going. Okay, so let's start off with region 1. So region 1 is this rectangular region. How do I compute the area of that? Let's do the formulas. Let's actually write it out. How would you compute the area of this box number 1? How do you do that? Base times height. Okay, and what is the base and what is the height? 80 by 120. Does everybody see that? Okay. I left my notes where I had my cheat sheet and the answer at the office. I'm going to need your help on this one. So we'll say 120 by 80. And so 120 times 80 is what? 9,600. Do I have a second on that? Okay. All right. All right, how about region 2? Okay, what's the area of this, this triangle? How do we compute the area of a triangle? 1/2 base times height. So 1/2 of base, which is 120, times the height, which is 60, right? So 1/2 base times height. And what is that? 3,600. Do I have a second on that? All right. How about region 3? Okay. Region 3 is this semicircular region. How do I compute the, well, first off, how do I compute the area of a circle? Pi r squared. So maybe the area of a semicircle is pi r squared over 2, right? So what's the radius of this region number 3? What's the radius of that? 60, right? It's 120 over 2, right? 120 is the diameter, right? So this part right here, this is going to be pi over 2 times 120 over 2 squared, right? Anybody have an answer on that? We'll say like 2 decimal places. It's because it's got a pi in there. Oh, come on. Everybody should have their Casio FX115ES Plus or equivalent calculator with them, especially in Engineering 213. Anybody have an answer for this? Y'all gonna have to speak up. I can't hear you. There we go. That's a way of seconding it. 5654.87. Okay. All right. Region 4. Now, how am I going to compute the area of region 4? What's the radius. Well, I guess I didn't need to put 120 over 2. It indicated that it was 60 in the schematics. I guess I could just put 60. All right. What's the area of region 4 going to be? Pi r squared. What's the radius of this circle? 40. So it's what? Pi times 40 squared? Or I missed something? There you go. Negative pi 40 squared. And what's that? Say it again. Well, times pi. Right? So there we go. Is that fair? Am I okay? Everybody okay with this? All right. Okay. Now I want to show you something. Oh, hit my little tab here on my little incline. Okay. All right. Hopefully this is simple, but this shouldn't be too complicated, right? Okay. Now, what we're going to do is we're going to do a series of calculations for each region, and what I'm going to do here at the bottom is I'm going to report the sum. Okay? Now, I'm not going to sum every column. I'm only going to sum the columns that I need. So I am going to need the area column, so I'm going to add up these 4 values. Okay? So don't forget that this is negative, okay? Oh, hold on. I need to learn how to operate my calculator. All right. Anybody got an answer for me? For this column? Do I have a second on that? Good. Okay. All right. That's exactly right. Okay. Somebody pick an axis. Which axis do you want to do first? X or Y? It doesn't matter. Want to do X? Let's do X. Okay. So what I'm going to do is I'm going to create a new column here. I'm going to call it X, and these are going to be in millimeters. Okay. Now, let's pay attention. All right. This is the origin right here. Okay. Let me draw that in big red marker right here. I might call that the datum because that's where I'm referencing everything. Okay, now I want you to help me out with something. All right, let's look at region 1. Region 1 is this rectangle, right? All right, so help me out. Everybody pay attention. This is the rectangle. Would you agree that where my laser is pointing is about the center of that rectangle? Along the x-axis, from my origin, how far do I have to travel to get the centroid, to get to the center of that rectangle? Half the distance, right? So if this is 120, I need to travel 120 over 2, which is 60. Is that a fair statement? Everybody okay with that? All right. Let's keep going then. Now, the triangle. Oh, that's interesting. All right. Now, the triangle. How far do you need to travel there? Well, if you don't know, that's why we have these lovely centroid references. And whenever you have a triangle, and it doesn't matter if it's, some acute or obtuse triangle, or if it's a right triangle, from the large end, you travel up this distance right here, which is h over 3, okay? So I propose that for shape number 2, right, shape number 2, the centroid is about right there, and along the x-axis, how far do I have to travel to get to the centroid of shape number 2? I propose you go 120 over 3, right? So 120 over 3, and this is what you derived on your homework assignment. This is 40. All right, with me so far? Okay, let's take shape number 3. How far is it along the x-axis for shape 3 from the datum to the center of that semicircle? 120 over 2. How about shape number 4? It's the same distance, right? I'm talking along the x-axis, right? For example, if I'm talking about shape 3, now first off, we don't know exactly how far up this is yet. So let's say this is the centroid of shape 3, but I'm asking for this distance right here. This is the distance I'm looking for. This is x3. And how far is that distance? 120 over 2. This is 120 over 2, which is 60. And same thing here. This is 120 over 2, which is 60. Am I going too fast, or does that make sense? Everybody with me so far? Okay. If you're okay with that, we can go ahead and compute one of our coordinates right now, okay? I have an area column, I have an x column, I'm now going to do this. And how do you do that? You just use cell by cell. So for example, this first one, what is 9,600 times 60? It's going to be big. That's okay. What about this next one? 3,600 times 40. Right? This next one. This times this. So we're doing this times that. What do we got? $56.54 plus $56.54 times 60. So come on, somebody out there's got it. 339. There we go. There we go. 339, 292.01. And the last one, what's that times that? And what was that keyword you said? Negative. All right. Everybody okay with this? Now what I'm going to do is I'm going to sum this. So somebody check me, but I'm getting 757,699. Is anybody else getting the same thing I am? Okay, I saw one person give me a thumbs up. Anybody else? Okay. Why did I do that? Because I propose that our centroid formula is this. It's just our moments divided by our forces. Only instead of moments of forces, we're doing moments of area. Areas and moments of area. That's all this is. So X bar is 757, 699.11 millimeters to the third. That's the unit system because we're taking millimeters times millimeters, divided by the area, millimeters squared, and we're getting what are we getting? We'll say 2 decimal places. There we go. There's one of them, right there. Now we're going to do the Y-bar one, but we're going to have some additional challenges with the Y-bar one that we need to be aware of, but we'll take it one step at a time. Does this make sense? Hopefully this isn't hard, you know. Hopefully this is straightforward. Okay, let's do Y-bar. Now I'm going to be a little bit squunched here. So what we're going to do, oh, wait, hold on. Let's just rewrite it. Bear with me. Whoop. Not that. Hold on. There we go. That's a little better. All right. Okay. Okay. So that we're referencing the same thing, the same system that we did before, let me drag this over here so that we can kind of see what we're looking at. Man, that's kind of sloppy, I know. Oh. That's a little better. Okay. So now what we're going to do is we're going to determine our y distances. Okay? Now, remember how it's split up, right? We had sort of a line going through like that. And so shape number 1 was the rectangle. So remember, we're also referencing our coordinates from this datum. So in this case, what we're doing is we're asking how far the centroid is from that red line, up and down. Okay? So help me out. How far is it from the from our reference axis, from our datum, to the center of that rectangle? Remember, we're looking at shape number 1, which in this case is that region right there. How would I determine the measurement from this line to the center of that rectangle, which is like right there? I promise it's not a trick question. There we go, 40. It's just 80 over 2. Am I going too fast? Is that everybody okay with this? If you got a question, don't hesitate. Everybody good? All right. Now, let's take this triangle. How far is it from this red line to the centroid of that triangle? Again, we're trying to determine the centroid of the whole thing, and so we're referencing the centroid of each of these basic shapes. 20 millimeters, but is it 20? Negative 20, because we're going down. We have to respect our coordinate system. So negative 60 over 3. Okay. Now, I'm actually going to skip this semicircle. I'm going to skip that. I want to do shape number 4. I want to do this hole. How far is it from the red line to the centroid of that hole, that circular hole? Okay, 80. That's easy. All right. Now let's talk about this semicircle. Let's talk about this. All right. Now, I have here a little reference. This is my centroid reference. And let's just see if we can pay attention to what's going on here. So I have this semicircular area right here. And what my centroid reference is telling me is that if I want this distance y bar, the distance from the bottom to the centroid of this shape, it's 4r over 3 pi. Does everybody see that? So that's the money right there, 4r over 3 pi. So is this 4r over 3 pi? Do I put 4r over 3 pi right there? Somebody's shaking their head no. Why? Well, yeah, I mean...
Don't you have to add 80 to it?
That's the answer I was looking for. I'm going to start giving some more homework problems in terms of x just because of that. Solve for this. No, but that's exactly right. We're referencing with respect to the same coordinate system. This will tell you where the centroid is with respect to this line. But if I want it with respect to our common coordinate system, I have to shift that up, right? So I propose that this distance right here is 80 plus 4r over 3 pi. And I ought to just leave it as r. Just, what is r? I'm asking you. No. No, hold on. Let's talk about that. We're looking at shape number 3. This is shape number 3. It's this entire semicircular region. What is the radius of shape 3? 60. There we go. So what is 80 plus 4r over 3 pi? I couldn't help it. Say it again. 105.5. Do I have a second on that? I'll hold on. I'll do that. Is that okay? Is this making sense? All right. So now what I'm going to do, and I'm going to delete this so that it's not in my way. Now what I can do is YA. So what do? Row times row. So what's 9,600 times 40? It's 384. 3,600 times 20, 72,000. Did I forget something? Negative 72,000. That's exactly right. All right, now we got that hullabaloo times this hullabaloo. I know it's a very technical term, isn't it? It's a bunch of stuff about things and items. What did we get? Okay, so what we're doing, we did that times that, then we're doing this times this. Does anybody have an answer for me on that one? I want to make sure I'm doing it right. That, and I want to make sure you all are awake. What? 12. That's not correct. Okay, yeah. I basically kind of got the same thing. I think mine, I had a little bit of, I was tracking my decimals a little bit. I had this, but if you're getting like 596 something, we're about in that same boat. But I was like putting the exact values in. And this times 80, let's see. I'm getting 402.123.86. Is that what you're getting?
Yeah.
Okay. So that minus that plus that plus that. I'm getting like 1,000,003. Yes, it should. Oh, thank you. You are exactly right. So that, hold on, that minus that plus that minus, that's negative. So 506,265. Somebody say that's better. I'm just going to put it at one decimal place. What do you think about that? No, I got to leave it at 2. All right. So now what we can do is and if you're wondering what this is basically just a weighted average. So the idea is that if I wanted to idealize the weight of this little bracket, I could idealize it as a single vector at the coordinates of the centroid. What are the coordinates of the centroid? Well, we know the x bar coordinate. Now we can compute y bar. And that's cubic millimeters over square millimeters and we get y bar of hold on. Oh, that's what happens when you're doing this on the fly. Come on. Anybody got an answer for me on that? 36.64. Do I have a second? Okay, I'm not gonna worry about that. All right. All right. Okay. Today, so far, or let me stop for a sec. Anybody have any questions about the process, about the algorithm? It should be pretty simple. Today is really sort of a plug and chug lecture because what I want you to understand today is the process of how to do this. Okay? And I'm going to say a few things before we call it. Right now, all I'm interested in is your ability to, if I give you a region, locate the centroid. And that, right now, is all I care about. Later on, in some of your engineering courses, the location of the centroid, like many of your later professors aren't going to like go through this. They're going to say, okay, can you compute it? Yeah, okay. Now let's talk about where, why it's important. And you're going to find that it shows up in all sorts of different areas in engineering. For example, being able to determine the centroid of a cross-section, let's say in a boat, will help you determine whether or not the boat will be stable under floating conditions. If I give you an I-beam, being able to determine where the centroid of that I shape is will tell you where the bending stress is 0. Everything above the centroid, you'll experience, say, compression. Maybe below the centroid, you'll experience tension. This is stuff you'll learn next semester. If you have a beam subjected to distributed loads instead of point loads, how do you handle those distributed loads? You handle them by locating the centroid. So what you're going to see, again, today was a very rote sort of plug and chug homework. You're going to see later how the centroid pops up, not just later on in this course, but throughout your academic careers. You're going to see it quite a bit, okay? We've done a lot of plugging and chugging, and we did not get 12. We got 36.64. I'm just kidding. We'll use this stuff later on in our next lecture and probably in a few more lectures throughout the semester. That's all I got. I will see you all on Wednesday.